Hello, and welcome back to the Mechanochemistry discussions. This seminar series is hosted by the NSF-funded Center for Mechanical Controlled Chemistry, or the CMCC. I'm Ashley Martini. As always, the goal of the seminar series is to bring our community together. The seminars stream live on the third Thursday of every month at 11 a.m. Eastern. They are also available to watch anytime on the YouTube channel. Also on the YouTube channel, we have all of our previous speakers as part of the seminar series, and I encourage you to check them out. We also have some excellent speakers planned for the upcoming months, and we hope that you will join us for all of them. Before we get started, a few quick thank yous. First, Dr. James Batiste, the Center Director, Jennifer Belsick, the Center's Administrative Coordinator, and two CMCC students without whom the seminar would not happen, Katie Floyd and Ryan Kwok. Please do continue to follow us and keep track of us on our YouTube channel at CMCC Mechanochemistry Discussions. Also, a few quick guidelines. The seminar is being recorded. If you have any questions during the webinar, you can either email them to us at cmccdiscussions@gmail.com, or you can post them directly into the YouTube channel. Either way, they will be propagated to the speaker at the end of the seminar. Without further ado, it is my pleasure to welcome today's speaker, Dr. Matthew Golder. Dr. Golder received his bachelor's in chemistry from the University of Rochester in 2010, where he conducted organometallic catalysis research with Professor Patrick Holland. Following graduation, he moved back to his home city of Boston, where he began graduate school in the lab of Professor Ramesh Jousty at Boston University. He relocated with the lab to the University of Oregon in 2014, where he earned his PhD in chemistry in 2015. His work on carbon nanohoop synthesis was recognized by a 2016 IUPAC Solvay International Award for Young Chemists. Dr. Golder was then an NIH NRSA postdoctoral fellow in Professor Jeremiah Johnson's laboratory at MIT, where he worked on the synthesis of polymer drug delivery agents and unimolecular macromolecules. He began his independent career in the Department of Chemistry at the University of Washington in 2019. His group works at the interface of physical organic chemistry and polymer science to explore novel structural motifs to solve broad challenges centered on sustainability, engineering, and energy. Dr. Golder is the recipient of a Theme Chemistry Journal Award, an NSF Career Award, and the Army Research Office Young Investigator Program Award. And he's an ACS Division of Organic Chemistry Young Investigator with an ACMS PMSE Early Investigator. It is my pleasure to welcome today's seminar speaker, Dr. Matthew Golder.
All right, thanks so much for the invitation from the NSF CMCC. I'm really excited to share some of my lab's work today, centered around the interface of mechanochemical transformations in soft polymeric materials. And a lot of the inspiration in our research group at the University of Washington is really centered around how polymers and plastics shape our lives. So we can see a variety of different types of commodity plastics here, ranging from the PET in your water bottles in the top left, all the way down through the polystyrene in your coffee cups in the bottom right. And if you look carefully, you can see a number of these intricate recycling symbols, which suggest some amount of sustainability within these materials. Much of what my group is interested in, and that I'll share in the later half of today's talk, is really focused on exploiting the recyclability and the sustainability of some of these materials to create new types of transformations and ways to reuse and repurpose these commodity plastics. Much of what we're interested in as well at the forefront of new types of soft materials is thinking about how molecular structure, right? The intricate arrangement of atoms and molecules in a repeating polymeric chain. And we'll have a little bit of a crash course on polymer synthesis and chemistry in just a little bit. How all of those factors from a synthetic, organic, and a macromolecular standpoint really allows us to access these new types of materials for clean energy, multi-layer packaging, thinking about keeping food fresh for long periods of time, new methods to build constructs from the bottom up, and even emissive materials like those found in your TV screen. So a little bit of an overview about my research group before we dive into today's talk. I started at the University of Washington at the end of 2019. We're a synthetic, organic, and polymer chemistry group with a large emphasis in mechanochemistry. So while we think a little bit about polymer methodology from the molecular level and from the catalysis level, what I really am excited to share with you today are two short vignettes, first centered around the use of mechano-redox catalysis to access polymers from the bottom up, and then thinking about that sustainability or polymer upcycling aspect that I alluded to a few slides ago to share how we can interface mechanochemical transformation for increased sustainability to try and solve the plastic waste problem. So I would be remiss to not share at least a little bit about how my group thinks about polymer chemistry at the interface of mechanochemistry. Again, as a macromolecular scientist, we think a lot about how traditionally mechanical force is used to destroy materials, right? And here we see this wrecking ball breaking down this brick wall, right? And there's at least in the polymer science world, right? There's a few ways to think about how mechanical force can be transpired into soft materials. Right? There's this whole field of mechanophore chemistry pioneered by Jeff Moore and many others in the field, where you can think about some type of soft material with engineered chemically responsive units that will give some type of a readout in the presence of exogenous mechanical force, right? Maybe a change in color or releasing the cargo, for example. And this is in stark contrast to the rich field of mechanochemical synthesis, where we can think about using force to forge bonds. For those interested in learning more about how you can build these really, really large macromolecular structures using mechanochemistry, I'll refer you to this great recent ChemSoc review. So what we're really interested in doing here, right, is as a polymer scientist, we're interested in using a traditionally destructive stimulus to construct and control materials, right? With this wrecking ball photo here, we can really think about mechanical force, at least from a first approximation with conventional wisdom. Right, that mechanical force is really going to be something that stretches polymer chains out, and this is known from the days of Staudinger almost 100 years ago now. And at some point, you'll end up with these macroscopic radicals that can go on and do further chemistry. But at the end of the day, you're breaking carbon-carbon or carbon heteroatom bonds along the backbone. And that's not what we want to do here. We want to use mechanical force to build materials from the bottom up, or control the functionality of these soft materials without concomitant chain decision. So the stories that I'm going to tell you about today are all going to be centered around using a traditional destructive stimulus to construct and control soft materials. So just a little bit of a crash course on the first half of our talk for today. Thinking about how kinetics can control polymer chain structure, right? So these are your polystyrene coffee cup lids, your polyacrylate adhesives, etc. These are all thermoplastic materials that can be constructed from individual unsaturated vinyl monomers through single electron radical processes. The industry favorite FRP, or free radical polymerization, involves typically with a thermally labile initiator, the generation of some small amount of free radical initiating species, and this is governed by a particular rate constant Ki. This starts to interact with your unsaturated monomers, and then you engage in propagation steps. In this case, propagation is really, really fast relative to initiation and chain termination events. So you end up with really, really high molecular weights at short monomer conversions. And then this starts to taper out as a function of time. We'll talk a little bit more about what molecular weight on the left-hand side and this dispersity in red on the right-hand side mean in just a bit. This is in stark contrast to RDRP, which is reversible deactivatable radical polymerization. This is just a fancy way of saying that we can get really good control over when chains are growing. So you can imagine this is analogous to a 5-lane freeway where each lane on the on-ramp to get onto I-5, for example, is governed by a red light or a green light. And each car is staggered so you don't end up with all of the cars going onto the freeway at the same time. So this allows for a very small amount of my polymer to grow at any one time, but most of the time the red light is on and those chains are dormant. So you have incremental growth pretty uniformly across all of my growing polymer chains. In order for this to occur, initiation has to be really, really fast relative to chain propagation. You can see here that you have a linear relationship between molecular weight and monomer conversion, and then this term called the dispersity ends up being fairly low at high monomer conversion. So just to reference some of these terms and kind of break them down into more tangible bytes, molecular weight for our purposes is just going to be the number average molar mass, aka the arithmetic mean. So we're going to make a lot of different sizes of polymer chains, and we're going to sum up the number of repeat units in each particular chain and divide by the number of chains to get some particular arithmetic mean. This term dispersity in red gives me a measure of the homogeneity of chain length. You can think about a protein as a polymer that's very, very well defined. All of the chains of a particular protein for a particular biological function have exactly the same length, and that means that I have a dispersity of 1.0. In practice, these free radical polymerizations end up with dispersities around 1.5 to 2. These more controlled processes have lowered dispersities starting to approach 1. Both of these measures, both molar mass and dispersity, are going to be measured in the subsequent slides using a technique called gel permeation chromatography or size exclusion chromatography. And this is going to separate out molecules based off of their size. So going through a size exclusion column, molecules that are really, really large will elute faster as they don't get trapped in the pores. Molecules that are much smaller will get trapped in the pores more readily and traverse through the column much slower. Okay, so now that we have a little bit of a crash course on how we're going to think about building these polymers from the bottom up using radical polymerizations, I want to introduce some of the current shortcomings to traditional solution state processes. I mentioned that many solution state radical polymerizations are initiated with some type of exogenous heat source, thermal energy, for example. And even some of the more modern techniques using either light or photochemistry or electrochemistry are all reliant on solution state processes. And when you start thinking about monomers that absorb light or opaque composites that scatter light, or in particular solubility limited building blocks or monomers that don't dissolve in a common solvent, this is where some of traditional solution state radical polymerizations start to break down. And where we really think that mechanical energy or mechanochemistry can start to solve some of these problems. So the concept that we're after here, mechanoredox catalysis, invokes these metal oxide nanoparticles that are piezoelectric in nature. So you can take these metal oxide nanoparticles and exert an exogenous mechanical force or stress. You end up with this highly polarized state that is capable of undergoing single electron transfer to some type of acceptor, and then we can close the catalytic cycle through back electron donation to fill that hole. So the first vignette that I want to tell you a little bit about is all centered around the concept of mechanoredox catalysis, using exogenous mechanical force to perform free and controlled radical polymerization. And this is all work done by Sarah, who's a 5th-year graduate student in the group, and Pragya, who is a former postdoc in our group. So these piezoelectric materials I alluded to on the previous slide, right, are these metal oxides that become polarized under stress. And that's because they have this non-centrosymmetric lattice structure. So in this case, we have zinc oxide on the left and barium titanate on the right. And the way that we can think about this is the electric polarization of this material is going to be proportional to the applied stress and some type of piezoelectric coefficient that we're going to term D. Right, so as I increase the stress, potentially from increasing the exogenous force, we can think about increasing the polarization. Each coefficient here is going to be specific to a particular type of material of a particular lattice structure. So as we switch from, for example, zinc oxide to barium titanate, we may expect to see different results in the chemistry. So in the lab, we can think about performing these prototypical reactions either in solution using an ultrasonication bath, where low frequency ultrasound produces cavitation bubbles within our solvent media. And the collapse of these bubbles results in tremendous amounts of shear force. This isn't what I'm going to focus on today. This is what some of the field got started on, what we got started on as well. What I really want to focus on today instead is our interest in ball mill grinding, right? For those less familiar with ball milling, this looks a little bit like a glorified paint shaker. You can adjust the frequency at which these arms oscillate back and forth, and you end up with these repetitive compression forces as not only the contents, but also one or more ball bearings within these steel jars mix back and forth. And again, I want to emphasize here that the first part of this talk is really going to be focused on making soft materials using instruments that are typically used down to break materials. Right, we typically think about mechanochemical ball milling in its traditional sense as a way to, for example, grind rocks or perovskites into particular small particle sizes. In our case here, we're really interested in using this strictly as an energy source to drive subsequent mechanochemical transformation. And I would be remiss not to mention that this first work that I'm going to share is really building off of the backbone of Aaron Etzer-Kahn's group and work from Chris Metajeski from about 5 or 7 years ago or so now. This is a particular type of reversible deactivatable radical polymerization called ATRP. I'm not going to go into all of the nitty-gritty chemistry here, but you can think about this as a way to get really, really low dispersities, really good control over your target molar mass. All 3 of these examples here, which you can find in the references below, invoke either barium titanate or zinc oxide. They're all using exogenous ultrasound, all in solution of polar aprotic solvent. They can control the molar mass and dispersity. And this was one of or three examples of some real seminal work in the field. And around the time that my group got started, and we started thinking about some of these problems in traditional radical chemistry, right? We were really interested in mechanochemical ball milling for specifically the problems that I laid out a few slides ago, thinking about ways to access soft materials from the bottom up that might not be accessible in solution. And this paper came out from Kubota and Ito that involved the mechano-redox reduction of these aryl diazonium salts and subsequent trapping with either a heterocycle or borylating agent. We were interested in this type of transformation here. We were less excited about potential safety concerns with the mechanochemical ball milling of these aryl diazoniums, but we thought that there could be some promise here. in a subsequent polymerization reaction. Again, thinking about aryl radicals as a way to kick off or initiate subsequent radical polymerization processes. So we eventually settled on these diaryl iodonium salts. These are aryl radical precursors, much like the aryl diazoniums, with a much better safety profile. And the idea here was that the exogenous mechanical force from mechanochemical ball milling would lead to reduction of the iodonium salt. The subsequent aryl radical could kick off polymerization, and we would end up with these polyacrylates or polymethacrylates. I want to point out that we're adding a really, really small amount of solvent here. In this case, dimethylformamide, which is a polar A product solvent. We're under liquid-assisted grinding conditions, so we're adding just a few drops of solvent to each reaction mixture. We end up with these really, really high molar masses. This is just uncontrolled free radical polymerization. Dispersities here are perhaps a bit lower than expected for free radical polymerization. We think that there could be some mechanochemical chain cleavage here at the high molecular weight end. But overall, these are really, really high molar masses that are oftentimes difficult to achieve in solution. And we think that some of the viscosity profiles here that are generated within the ball milling jars lead to a reduction in chain termination. Looking at these reactions pictorially, right, we start with something that sort of looks like sand in a puddle with a single ball bearing here. And after we shake around for a bit, we end up with this essentially polymer composite. We can dissolve the polymer up and precipitate out the particles and reuse and recycle them in subsequent reactions. But the real take-home point of this slide is that in addition to the increased viscosity and the presumed decreased rate of chain termination, we think that in addition to the DMF acting as a reaction medium for this reaction to proceed, we also think that it's plasticizing the material along the way. And it's lowering the glass transition temperature, and that reduces the rate of chain fission. And this is work that was all outlined by Peterson and Choi a few years ago in this nice macromolecules paper that correlates a particular polymer's glass transition temperature to the rate of chain fission. We can set these free radical polymerizations up either under a nitrogen atmosphere in the glove box or under air on the benchtop. But what we noticed is that the kinetic profiles for monomer consumption, so monomer consumption is on the y-axis here and reaction time is on the x-axis. You have this huge incubation period for just over 2 hours when we set these reactions up under air. And then we get really, really rapid conversion within the course of a few minutes. This is in stark contrast to sort of the pseudo first order kinetics that we see under a nitrogen atmosphere in orange. What we think is happening, we don't have any experimental evidence from our own experiment here, but some recent work in the literature suggests that O2 oxidation to superoxide may limit some of our conversion at early time points, in that there is some rate associated with scrubbing in quotes of the atmosphere of O2, and once all of the O2 is scrubbed from the headspace of our sealed vessel, the radical processes can begin to proceed. Mechanistically, we are confident that the diaryl iodonium salt is our initiating species. We can perform the mechano-redox reduction of these diaryl iodonium salts in the presence of an H atom transfer agent, such as this cyclohexyl captain. And we would expect the generation of both iodobenzene and benzene following H atom transfer. And that's exactly what we see. We can mill this for about an hour, and we see 50% conversion of our iodonium salt with appreciable formation of both iodobenzene and benzene by NMR spectroscopy. And if we mill in the absence of barium titanate, we see virtually no conversion. and subsequently virtually no production of those small molecule products. These free radical polymerizations are inherently more sustainable, at least at a first approximation level in lab scale, right? This isn't talking about an industrial process. We're just comparing apples to apples here in our own lab. Thinking about the expedited profile in the ball mill, we can run the reaction for about 3 hours. We're not applying exogenous heat. We're using about 1/4 of a kilowatt hour for this entire process to occur. We've been able to run these in a benchtop vortexer as well. The reactions take a little bit longer, much less energy is used in the process. This is in stark contrast to the 20 hours at 70 degrees C that would be needed for these reactions to reach complete conversion. And as a result, that uses at least 3 times as much energy. So again, this isn't to say that things will scale exactly the same way on an industrial process with something like a drum mill, but at least on a small lab scale level, I think it definitely demonstrates some of the advantages of mechanochemistry. This was all done by Wasim, who is a former REU student in our group. We've been able to recapitulate those free radical processes to a particular type of controlled radical process called RAFT. Again, these controlled radical processes ensure that only a small amount of chains are growing or propagating at any one time, and the majority of them are captured dormant. Again, this is that freeway red light, green light analogy that I made towards the beginning of the talk. And what's really nice about RAFT and these controlled radical methods is it allows us to access sequence controlled polymers. So I can, for example, incorporate a tert-butyl acrylate monomer here, and that's given by this orange trace, and then I can add in an N-butyl acrylate monomer, and I can continue to grow. So I have what's called a block of tert-butyl acrylate, and then a block of poly N-butyl acrylate, and that's seen by this nice peak-to-peak conversion in my size exclusion chromatogram, right? Molecules that are larger elute sooner, molecules that are smaller elute later. So it's done by Pragya, again, a former postdoc in the group, and Kato, who is a former visiting student from Japan. Okay, so now comes some of the real highlight of this work, in my opinion at least, thinking about making fluorinated polymers without specialized reagents. And I'll share why some of these polymers are still important, even in the era of the moving away from the PFAS type materials. These types of fluorinated and semi-fluorinated materials in particular markets and particular industries still have a lot of potentially useful applications when used in moderation. But oftentimes the way that these types of polymers are made involves some type of fluorinated solvent or some type of exotic initiator, ligand, or chain transfer agent. So you have to add more types of fluorinated materials or catalysts or reagents into the mixture in order to help compatibilize your fluorinated building blocks with whatever else you're trying to include into your polymer chain. And we thought that mechanochemistry could potentially solve some of these problems. This was recently shown in this nice ChemSci paper from Tomislav and Jeju Kim, where using some of these same principles, we thought that we could access this semi-fluorinated polymer that contains both the hydrophilic building block here in blue and this orange semi-fluorinated block here in orange. You can see the same type of peak-to-peak transformation here. The upside down peak is just due to the fact that the refractive index of this material is lower than that of our mobile phase on our HPLC. But right, again, we have really nice chain extension here. We don't see a ton of broadening of our dispersity that would be indicative of mechanochemical chain decision. And this really enables a fast ion sustainable method to access these types of exotic materials. A polymer science way of assessing the microstructure of these materials, and proving that we actually have a block of hydrophilic building block and then a block of fluorinated building block, is to use a technique called small angle X-ray scattering. And because these are highly immiscible, we would expect these to phase separate in the bulk, and it's known that they'll form well-ordered nanostructures, and we can probe that with SACs. And that's exactly what's shown here on the top right. It's shown that these materials self-assemble into well-defined lamellae. This is in stark contrast to when you go through and make a statistically random copolymer by adding all of the monomer in at once, right? So I add the hydrophilic monomer and the fluorinated monomer to the same jar, and I mill for a few hours. I would expect a random copolymer that doesn't show any self-assembly on the nanoscale. So this demonstrates that we're not getting two types of homopolymers that are mechanochemically cleaving and coming back together at random. We really have good control over a sequence here, and mechanochemical chain decision seems to be a very minor component of this process, if it exists at all. These materials, again, despite all of the concerns over PFAS derived materials, the incorporation of small amounts of fluorinated materials for things such as photolithography, photomasks, batteries, membranes, etc. There's still a lot of utility as we can continue to build new types of materials from the bottom up. So I think what I've shown so far, right, is that mixing mechanics can really impact reactivity, right? Much in the way that kneading pasta dough by hand versus in a KitchenAid mixer can lead to wildly different results. Much in the way that stirring a martini and shaking a martini can also lead to wildly different results. I think that this first vignette here has really demonstrated that mechanochemistry has potential to access materials that are somewhere between challenging to impossible to access with traditional solution state methods. And where I want to go from there is some of our lab's interest in tackling the plastic waste problem. I just showed a lot of work on how we're interested in building new types of soft materials and plastics from the bottom up. But what about the plastics that are already out there? Things like polystyrene that are generated on the million metric ton scale each year, but are actually sparsely recycled. Polystyrene is probably the worst offender out there in terms of the percent of that type of plastic which is actually recycled. And the idea is that we can use some type of post-polymerization or chemical functionalization to this commodity plastic waste to add new types of functionality that might help us recycle or embed new properties. And I'll share some of the ideas in just a bit. This is all work that was performed by Morgan, who's a third-year graduate student in the group. So the real question that we want to ask here is if mechanochemistry can start to tackle some of the processing limitations with conventional post-polymerization modifications. Right, when you think about commercial and post-consumer plastic waste, we're oftentimes dealing with really high molar mass materials with really broad dispersities that have had all sorts of histories before they end up into the recycling plant. And thinking about unifying methods that can potentially process all of those different types of waste without concerns of solubility, contaminant additives on the downstream chemical processes is really, really important. What I want to emphasize is that you don't have to do a lot to the backbone of a polymer to really change its function. You can get minimal functionalization that can alter bulk properties. So in this case, we have polyethylene. This is an example from John Hartwig's group. The copper catalyzed emanation of the polyethylene backbone. And even at less than 2 mol% tagging, you can get drastic enhancement in downstream mechanical properties. This is work from Fredrickson and Siegelman that shows that you can actually tag two traditionally immiscible polymers. So in this case, polyethylene and isotactic polypropylene with positively charged and negatively charged groups, and you can form these ionic pairings in just really, really small amounts of those pairings, less than 1 to 5%, depending on the specific identities, can lead to complete compatibilization. And the ability to compatibilize these immiscible waste streams is a huge step forward in the broader problem of remediating plastic waste, right? If you have mixed waste streams and you start thinking about phase separating materials, being able to actually bring those materials together to form some new type of material is really, really impactful. So we think that mechanochemical ball milling coupled with post-polymerization modifications can potentially address some of these problems. There's many examples out there of these post-polymerization modifications of a variety of types of polymers in the ball mill. I'm just showing a handful of examples here. On the left, we have this imine condensation or a thiol SN2 type of reaction. You can think about some more commercially relevant polymers, polyethylene glycol on the top right, polyvinyl alcohol or PVC on the bottom right. What all of these processes share, though, is that these are really, really short milling times. Right, we're milling on the order of tens of minutes here, and that's because these are all really low barrier processes. Because of that, we don't have to think as hard about competing chain scission reactions. Right, that was the whole point of the liquid assisted grinding in our polymer synthesis towards the beginning of this talk. I mentioned at the very beginning that there's this whole idea from Staudinger and others that exogenous mechanical force can break down polymer chains into these macroscopic radicals. Right, and this was shown recently by Peterson and Choi. Right, you can look at this high molecular weight polystyrene and just sticking it into the ball mill. We quickly evolve down to what's called the limiting molecular weight. Right, so this is where polystyrene will break down into really small oligomers on the order of about 10 kilodaltons or so. This happens in just about 10 minutes. And in their work, they were able to show as they start to perturb the glass transition temperature of the polymer, you see a marked decrease in the rate of mechanochemical chain scission. As you increase the amount of exogenous plasticizer that you dope into the material, going from right to left, you also see a subsequent drop in glass transition temperature, which is what a plasticizer will do. And that also leads to a marked decrease in mechanochemical chain scission rate. So what we were after here was thinking about some type of mechanochemical post-polymerization modification approach that we could study not only on a small molecule model of polystyrene, such as bibenzyl, but then eventually apply to waste polystyrene. The specific method that we're after here is trifluoromethylation. And that's not because that trifluoromethylated polystyrene is the most useful material out there, but it really gives us a handle via 19F NMR spectroscopy for quantifying the amount of functionalization. So the goal here is to use 19F NMR spectroscopy, which is an extremely sensitive NMR nucleus, coupled with GPC to really assess how these two processes can compete, specifically in the context of post-consumer waste, right? Can we identify conditions that allow us to perform some high barrier post-polymerization modification process without a significant amount of concomitant chain scission? In addition, there are some applications to trifluoromethylated polystyrene, both in the coatings industry and the organic electronics industry. But in this case, we're, again, really interested in just the trifluoromethyl group as a nice functional handle for analytical purposes. We were really interested, again, in the use of post-consumer waste that are typically challenging with traditional chemical recycling methods, ones that include additives and dyes, for example. I mentioned towards the beginning, when we think about the manufacture of plastics under photochemical conditions, if you have opaque composites or absorbing monomers, it starts to shut down those photochemical processes. The same is true in solution state methods that introduce these exogenous dyes like you might have in this black coffee cup lid. And we thought that we might be able to start to modulate degradation, again, using liquid-assisted grinding. So we identified this trifluoromethylation reaction from Melanie Sanford's group that was reported about 15 years ago or so now. And we performed it both on bibenzyl in solution and under mechanochemical conditions. The idea here is that we're adding a gross excess of arine relative to our trifluoromethylating reagent. This gives us a max functionalization of 10 mole percent. So 100% yield would give us 10 mole percent. So if we set this up in solution under the standard conditions reported in the paper, we get about 8% mole or 8 mole percent functionalization, which equates to an 80% yield. Mechanochemically, we can run this for a lot shorter time in the ball mill using much less solvent, and we get still pretty good yield in about 5 to 6 mole percent functionalization. So they showed us that we could use these relatively unreactive arenes that are found in polystyrene just through the use of this bibenzyl model system. We then wanted to start to explore more relevant polystyrene substrates. So we selected a polystyrene that was above the limiting molecular weight. This is a 26 kilodalton polymer that has a glass transition temperature of about 101. And we saw that when we mixed in our liquid reagents, our small amount of lag solvent and our small amount of liquid trifluoromethylating reagent, and we mix them around for a bit, we see about a 30-degree decrease in glass transition temperature. So this was pretty good evidence to us that we could potentially plasticize our material just through this liquid-assisted grinding, and then based off of the work of Peterson and Choi, we presume that we, in turn, may be able to really cut down the rate of mechanochemical chain decision whilst still performing productive carbon-carbon bond formations for the post-polymerization modification. So thinking about this in another way, we can look at the GBC traces. We start with our initial 26 kilodalton polystyrene, so again, above the limiting molecular weight in the dotted blue line. In gold, we have the trace after we mill in the presence of our lag conditions. So we see no change in molar mass here at all, which is good, right? We're not getting mechanochemical chain decision to any appreciable degree. If we mill with just the solids, or if we just mill the polystyrene, we see a shift to longer retention time, which implies that we're starting to mechanochemically cleave the backbone, and we see an increase in dispersity as well. Right, so this was really good evidence that liquid-assisted grinding could potentially quell this reaction. Some work that I'm not going to have time to share today that Morgan did demonstrates that this trifluoromethylation works great on smaller polystyrene, including this 26 kilodalton material that I'm discussing on this slide. But where this gets really exciting is when we start thinking about using post-consumer and commercial waste. So we selected a variety of substrates here. On the left here, we have commercial beads. So these are beads that might be used in industrial processes. You can also use post-consumer material. This is this expanded polystyrene foam. Right, this is your packing peanuts or your cooler cartons. we can either take the foam and crush it up, or we can actually go through and precipitate the foam to remove any plasticizers, additives, etc. We can do exactly the same with a black coffee cup lid. We can either use the native material on the left, or we can go through and precipitate the material on the right. What you'll notice here, there's a small change in molar mass after we precipitate the material, and that's just due to the fact that we're artificially enriching either the higher or lower molecular weight region after precipitation, just depending on the particular conditions that we use. But perhaps more importantly, we see about a 10-degree decrease in glass transition temperature from a little bit above 100 down to about 90 to 95. And that, again, we surmise is due to the fact that we are removing at least some amount of the additives and plasticizers. These are all post-consumer proprietary blends, so we don't actually know what we're working with here. This is a little bit of a black box, but we know at least from the fact that we see a change in glass transition temperature that we're removing some amount of those additives. You can see here, at least with the black coffee cup lid, going from a black material to a colorless material is also good evidence. So I'm going to show you just an emblematic example of what we did from here to start putting these post-consumer materials into the ball mill, working off of this precipitated foam. So we're working with this high molar mass material where we've gone through and we've removed as much of the additives and plasticizers as we can. So we could take this roughly 100 kilodalton polymer, we could subject it to the same conditions in the ball mill for trifluoromethylation. Again, the math is worked out here such that our max functionalization is 10%. So we're using 10 mol% of the trifluoromethylating agent, so we can get a maximum of 10 mol% tagging on our backbone here. So we can go through and change the amount of lag solvent that we're adding. And we saw that if we add a small amount of lag solvent, we get about 1 mol% tagging, which for things like ionic compatibilization is actually enough. Again, we don't need a lot of functionalization here to have a huge impact on some of the downstream applications and properties. But what I want to emphasize here is that we see this huge decrease in molar mass. So this small amount of lag solvent, up to about 0.6 microliters per meg of substrate, is not quite enough to really quell that chain decision. And on the other end, we actually start to see a little bit less chain decision as we get up to about 1 to 1.2 microliters per meg. But we start to shut down the productive reaction as well as we start to add too much lag solvent. We settled on a sweet spot in the middle here. Somewhere between about 0.8 and 1 seemed to be the sweet spot where we were getting about a 1 mol% tagging. We still saw a little bit, about a 20 to 30% decrease in molar mass, but we thought that this would be a good place to work from. Right, but this when you start to apply this broadly, we actually started to notice some more problems, right? So we can take this precipitated EPS foam, we mill it in the presence of 0.8 microliters per meg of solvent. We see about a 30% decrease in molar mass. But when we apply the same conditions to the precipitated lid, we start to mill it and we actually end up with close to the limiting molecular weight. So this tells us that, the processing here of these post-consumer wastes might be a little bit different, and the broad application of these conditions across the board may be a little bit more complex than meets the eye. This is in stark contrast to when we use the native waste. Actually, the native waste, we were able to get about 0.3 mol% tagging. So less than on the precipitated foam, but we see only about a 15 to 20% reduction in molar mass when we use the same 0.8 milliliters per meg. But what was really interesting was that what we assumed would be the absolute worst substrate, the coffee cup lid with dyes, right? This is the only dyed plastic here. This worked the best. We saw virtually no change in molar mass, about 0.5 to 1 mol% tagging. In this case, when we use about 1 so we thought that there was something interesting here, and I'll kind of share just the results of many months of work. Right, we can do this with the commercial polystyrene as well. 1 microliter per meg gives us about 100 kilodaltons. The moral of the story here is lag is not enough. We can add this liquid assisted grinding solvent in, and it helps to some degree depending on the substrate. It promotes the chemistry to some degree, but it's not the end all be all for this particular process. So what we settled on was a synergy between liquid assisted grinding and the addition of exogenous plasticizers. We thought that this could have been why the coffee cup lid worked so well in the first place. Perhaps it was inherently more plasticized in the native form. So we went through and we doped in a common plasticizer, this dioctyl terephthalate, to our native waste. We saw a marked increase in both mole percent functionalization as well as control over molar mass. All right, so we can take the same native foam. We get about 1 mole percent tagging in the presence of the 2 weight percent DOTP. So a really small amount of plasticizers being added in, and we retain really nice control over molar mass. The coffee cup lid worked pretty well as is, so we didn't touch those conditions at all. Same with the commercial polystyrene, just a small change in molar mass in the presence of our DOTP. All right, so with that, I just want to wrap up, and I hope that I've showed you some of our lab's work at the interface of polymeric materials and mechanochemistry. We started talking about mechano-redox catalysis and how we can use free and controlled radical polymerizations in the ball mill to build these soft materials from the bottom up. And then we finished up with our interest in polymer upcycling, thinking about using mechanochemistry as a way to modify post-consumer waste without the typical limitations employed by solution state chemistry. And as a unifying theme, that the concept of liquid assisted grinding and plasticization within ball milling allows us to outcompete chain scission with some type of productive bond formation, whether it's the backbone growth or growth along the periphery of an existing chain. I want to thank those who did the work. I gave them acknowledgements along the way, but just to reiterate, Sarah and Pragya and Kato and Wasim did a great job with the Mechano-redox polymerizations, and then Morgan and Sarah worked on the post-polymerization modification and upcycling work. And I'd be happy to answer any questions.
All right, thank you for that presentation. We'll take some questions from the audience. Let's start here. Could you clarify what you mean by lower barrier processes equals shorter milling times? Do you think that this is the activation energy of the reaction that is altered under mechanical conditions, or that other processes, such as mixing or lack of solvent, accelerate the reaction?
Yeah, that's a great question. I think we're not 100% sure. So I guess what I was going after with lower barrier processes, in amine condensation runs in solution at least at a lot lower temperature than something like the 90 degrees that we're running our trifluoromethylation at. So I think inherently the process that we're going after is a lot higher activation barrier and inherently has to mill for a lot longer. With that, what we're really after is an ability to control those rates of chain scissions such that we can control the rates at longer milling times to start thinking about higher barrier processes.
Okay, thank you. Here's another one. Do you ever have problems with polymerizations failing because the mixture gets sticky and dense and stops the ball from being able to move freely? If so, how do you address this challenge?
Yeah, that's a great question as well. We've noticed this a little bit more in the post-polymerization work. where the tackiness of the mixture within the milling jar can really impact both mixing and then downstream chemistry. In the case of the free and controlled radical polymerizations, we've had to play around a little bit with the concentration of lag solvent, but we haven't had too much trouble with mixing in those cases. And we've never really seen polymerizations fail because it gets too tacky.
Okay. All right, let's do another one. You mentioned that sometimes your polymers made mechanochemically can be nanostructures on the order of 25 nanometers. Does this change the polymer's material properties in a way that would be concerning for practical use?
Yeah, so I can maybe go back to that slide. It's actually going to be hard on Zoom. I'm not going to go back to that slide. I'll just describe it. So I guess the 25 nanometers is the domain spacing for those nano ordered lamellae structures. So in the bulk, they'll assemble, and you can probe that by SACs, and you can probe it by transmission electron microscopy. But in terms of bulk performance, I think that those are two completely different phenomena, and that there are people that are interested in correlating nano ordered structure to mechanical performance. But in this case, that's not necessarily what we're after, but we would expect the same trends to hold true.
Okay. Let's wrap up with one that I received in a couple different forms. This
Okay.
is about scale up, but I'll ask it in this form. Given that many polymers need to be made at large scales, how do you envision this chemistry being scaled up going forward? Do you have some ideas for the best method to scale, for example, ball mill, vortex mill, mixer, etc.?
Yeah, I think a lot of the ball millers out there have the same question, and there's probably more expertise in the CMCC than I can even begin to answer. I think a drum mill would be one potential route forward. Thinking about the same types of mechanical forces, at least from an organic chemist viewpoint. That's sort of my vision there. That's not something that we've necessarily explored, though.
All right, well, I will conclude by also saying that you have changed my view of mechanochemistry with your analogy of the martini, shaken versus stirred. So I am going to steal that from you going forward. But thank you again for your presentation. We appreciate it.
Thanks so much.
Thank you, Dr. Golder, for that outstanding presentation. And thank you so much for joining us. Just a reminder that all of our previous seminar speakers are available to watch anytime on the YouTube channel, and I encourage you to check them out. We also have some great seminar speakers planned for the upcoming months, and we hope that you will join us for all of them. Thank you again.